In this video, I'll be discussing an incomplete information game using the Tern-Trevally analogy. This example stems from the TV show Blue Planet 2, which explores life in the oceans. In one episode, small birds called terns are spotted breeding on a remote atoll in the Indian Ocean. The young chicks wait on land until they are ready to fly. Once they gain the confidence, they train over the shallow lagoons that either hover over the water to drink or float in the water to rest. On the other hand, we have giant trevallies who feed on the small birds. They capture the birds either by swimming up behind them or jumping out of the water to catch them whilst they're hovering. Birds can either be strong or weak flyers, and nature determines this. Nature can be thought of as a probability distribution over the types of flyer the bird is, and this is known by both the bird and the fish. The fish have just one type, and this is rational, meaning they would rather eat than go hungry. Strong flying birds are able to escape the fish more easily than the weak flying birds. The birds know what type of flyer they are, but the fish does not have this information. We can view this game in extensive form, where the dashed line denotes a simultaneous game, so neither player knows the other's choice of action before they pick their own. Nature decides the bird is a strong flyer with probability p, and a weak flyer with probability 1 minus p. Knowing its type, the bird then chooses to hover or float, whilst the fish decides whether to swim or jump. The payoff for the bird is positive, depending on how easy it was to escape, and negative if they were injured or captured. The payoff for the fish is positive if they caught the bird, and negative if they're still hungry. For example, a weak flyer that floats is easily caught by a jumping fish, leading to a payoff of minus 10 for the bird who is caught and 10 for the fish who goes away full. We can define the bird strategy as XY, where X is the action taken if the bird is a strong flyer and Y is the action taken if the bird is a weak flyer. For simplicity, we will say there is a 50% chance of the bird being a strong flyer and 50% chance of the bird being a weak flyer. We can create a normal form matrix to show the payoffs of each player. If the bird plays strategy HH, hover hover, and the fish plays strategy J, jump, then with probability p, the outcome will yield 2 minus 6, and with probability 1 minus p, the outcome will yield minus 3 minus 1. With this strategy, the bird will get utility minus 0.5, and the fish will get utility minus 3.5. We can fill out the rest of the matrix in the same way. From the matrix, we can see that J yields greater payoffs than S for the fish, so we can eliminate column S, as the fish is rational and strictly prefers J. Looking at column J, bird receives the highest payoff using strategy HH, giving us the Nash equilibrium HHJ. This means the bird would always hover, as it is easier to escape this way, and the fish would always choose jump, as it gives them the most opportunity to catch the bird. In reality, newly born chicks are not aware of the need to survive, and so have less incentive to hover. The most likely strategy would therefore be to hover if they are a strong flyer, and float if they are a weak flyer, leading to the overall outcome HFJ, as the fish would still jump because this gives it the greatest chance of catching the bird. The bird is worse off here than in Nash equilibrium, but the fish is better off as it gets to eat, which coincides with the natural food chain.